Srinivas, and it was great to come to India and find a Tyndall alumni. So I'm delighted to be here and to have been invited to speak to you. And I'm probably going to take you through a range of topics which are really maybe being presented just to put ideas out there rather than to come up with any deep conclusions. We are a large number of people from Tyndall. There's about 12 of us here this week with a stand outside. It might feel a bit like the Mughals coming across from Persia, but we're friendly. And I should also like to acknowledge Dr. Professor Veda Sandeep for all the work she has done in actually bringing us here to India and looking after us at every turn. So I just wanted to start by talking about Tyndall National Institute and just to give you a sense of, okay, where the work that I'm going to talk about is coming from. And some of my colleagues have spoken over the last few days, and they'll be speaking tomorrow as well. So you may have heard them and you get a sense. Anyhow, we're very much focused in the area of hardware, electronics, nanotechnology, photonics, MEMS, going all the way to quantum engineering, wireless communications, and energy. And I guess what's increasingly important today is you will see that electronics or information technology is ubiquitous. So, and you know, the UN Sustainable Development Goals are really important globally, and therefore we invest a lot of our time in developing and engaging with end users and customers to develop technologies in information communications, but micro and macro energy, agri-tech, food security, the environment, and health and life sciences. And that's really important in terms of delivering impact from research. So at the moment we have two large centres, micro nano systems and photonics. I head up the micro nano systems. And then we have underlying facilities in silicon 3.5, MEMS fabrication, test characterization, packaging, heterogeneous integration, and that amounts to about 200 million infrastructure. And the important thing, I guess, in our research environment is we do go from atoms to systems. So at the atomic level, developing models for materials that might be used in atomic layer deposition, figuring out the synthesis and processing of materials, range of semiconductor and MEMS devices, including sensors, and then a large amount of circuits, and ultimately systems. And the systems development are also typically with external parties who are embedded in the application sector that we're interested in, whether that's agriculture or medicine or energy or communications. So here's some data about Tyndall: 600 researchers, engineers, support staff, 250 million infrastructure, annual income about 45 million euro. 80% of that's from competitive funding. And we're very strong and very much engaged in EU funding. And in fact, recently, in the last 2 weeks, there's been an EU funding call for EU-India projects, and that could be quite interesting to pursue. We have about 150 graduate students, a large number of international clients, a large number of industry researchers in residence, with a significant amount of industry income. And our strategic plan is built, I've been there 40 years, and this is the simplest strategic plan I've ever had, so I can remember it. But you know, if you want to deliver impact from excellence, these are probably some, if not all, of the parameters that you need. You need to focus on research excellence that will have impact. You need to position yourself internationally to compete internationally. You need to develop people and culture and a culture of collaboration, but you have to develop the people from the time they come in as graduate students They are the next leaders. I mentioned to many of the graduate students who come in, I say to them, they're the future, I'm the past. And I think that's really important to understand the need to develop those people. Going forward, over the next number of years, we've got funding from government to double in size effectively. Double our income, ideally almost double the number of people, graduate students. And one really important parameter or metric there is to increase the number of female graduate students from 20% to 40%. We're currently at around 32%, but that's really critical in the age that we live in, that we are appropriately giving opportunities to everybody. Part of the development will be us moving from, can I use this guy here? This one? Okay. So part of our development over the next number of years will be expanding from this site here, on one side of the river, to this new site, and doubling the overall size of the campus, which is going to be a very exciting opportunity and demonstrates the confidence that the government has in us. I think this is a very important map, and we have come up with a phrase, Tindia. So this is our Tindia program. And what I'm showing you here is only about 50% of the Indian researchers and graduate students who are in Tyndall at present. And you can see they come from all over India. And what's really interesting is the female to male ratio is 40-60. So that's actually higher than our generic Tyndall-wide ratio of about 32% at the moment. And you will also notice there's a connection here between the Indian flag and the Irish flag. The white in the middle, I think, in both cases represents peace, which has eventually arrived in Ireland after many years. So I just wanted to introduce the idea of sensors. So, when I think of a sensor, I just think of a device that if I put a voltage across it, it will measure something. But that would actually be a dumb sensor. So if anybody wants to buy a sensor today, they expect it to be, fully powered. They probably want it to be somewhat intelligent, and it should be wireless. And you have plenty of examples of these in your home, remote controls, etc., that fall into that category. So the idea of a sensor then is actually it's a miniaturized system, and that's really important. And many companies who have been experts in sensors or experts in data processing, IC design and so on, are finding that they have to move from that hardware orientation to actually a solutions orientated business. And that's happening right across the world. And if you then talk about what we are trying to do in this space, I guess we're trying to develop technology, make and power the smart things for the 1 trillion sensor economy. So what is being proposed is that there's going to be 100 billion devices that will all have sensors on them in the future, each of them having 10 sensors. So if you ask the question, well, my mobile phone already has probably 10 sensors. So, we're starting in that direction. If you think of smart homes and so on, we're already starting in that direction. So what we are looking to do, though, is, if you're to do this, we need a sustainable Internet of Everything. And what we work from, as I said, atoms to systems. So starting with nanomaterials, delivering nanosensors, and many of those sensors need to be perhaps CMOS compatible at the moment, interface circuits for data processing communications, and we need energy to make them autonomous. So can we rely on batteries to support all of these sensors? We probably need to develop energy harvesting. And intelligence is going to be critical. And we talk about, the intelligence that we need at the edge of this Internet of Everything. And we actually talk about the edge of the edge. So it's going back to these dumb sensors that are no longer dumb, but they actually need to be able to collect data and make decisions locally in real time and very quickly without using a lot of energy. So here are 5 strategic research clusters in the Micro Nanosystems Centre, and I just wanted to bring your attention to this sort of way of describing the world of sensors, perhaps. So I think of in the body, on the body, and then around the body is everywhere else, in the built environment, in our natural environment, and so on. It's very simplistic, but it does present a useful model. So what I want to do now is I want to go through and just describe some of the technologies we've been working in. One of those is looking at microneedle technology, so that we can actually introduce, we can take fluids from the body, or we can introduce some sort of therapeutics drugs into the body. So we started working on this using micromachining of silicon, giving us microneedles. The devices here are about 300 microns in diameter here. No, actually 300 microns in height and about 100 microns diameter. And you can see the tip, really sharp tip on all of these. And then you can convert, you can use these as a master to actually get polymer-based microneedles that we also have used. And in fact, one of the School of Pharmacy that we worked with, they actually built molded microneedles out of a sugar solution that actually had a vaccine in the solution, so that you would actually get the microneedle to dissolve into the body with that vaccine. So what we're trying to do is actually introduce the microneedles into the epidermis, but we're replacing these very large needle syringes that go deeper into the body. And so you end up with no pain. You don't hit the nerves. So this would be a great opportunity. So now perhaps we can have a plaster that has a microneedle and we can put it on the body, and we can actually introduce vaccines very easily, or we can actually remove interstitial fluid and measure for cortisol, stress, and so on. And so ultimately you could actually transform this into, let's say, a plaster or a bandage that has all of this technology embedded in it, so that you end up with a smart theranostic system. The other area that's important, if I think about, I mentioned around the body, and one of my colleagues, a number of my colleagues have spoken in this area about agriculture 4.0, and I guess, there are a lot of talks about energy at the moment, about sustainability of the planet and so on, but food production is really critical right across the globe. And at the moment in Ireland, for instance, we have a lot of cows, dairy cows, so they're delivering milk, but they're actually contributing something like 30% to our overall CO2 emissions, which is causing us some problems. So there's a significant need to improve on that situation. So one of the team working on this is looking at the idea of in-the-field biochemical sensing. So why are we looking at that? Well, if you want to take existing systems for agriculture and to monitor in the field, usually you have to take samples, take them to a lab, wait 2 weeks, get the result back, and then do something. A farmer cannot afford to wait 2 weeks if they're going to be spreading any crops or fertilizer or anything like that. So what is needed then is some sort of electrochemical, biochemical nanosensors that can enable portable systems that actually the farmer could actually use. And so there's a lot of issues from a state-of-the-art point of view with these type of sensors. They need reagents, which means you need extra liquids, fluids. They need on-chip or reference electrodes. They need to be calibrated. While the electrochemistry can quantify, but it's very poor at identifying the chemical species. And there aren't cost-effective systems available that can go into the field. So what we have gone and done is looking at some of the issues, get rid of the reagents, and enable localized pH control by just varying voltages so that we can actually detect the various species, using stable on-chip reference electrodes, again by using polymer coatings to maintain chemical stability. More importantly, eliminate the need for calibration, and perhaps artificial intelligence, machine learning can be used here. And then using electrochemistry and surface chemistries that will identify the chemical species. So what we have been able to do is develop systems for field measurement, and in the end of the day, enable the end user, which is the farmer. So one example is in-field detection of potato plant disease. And this is a multidisciplinary problem. So we have the biochemical sensors, we have electronics, and then we have the end user who are Teagasc, the National Agricultural Research Centre in Ireland. And I mean, the great thing about this is what the team have managed to do is to be able to create a €90 portable device that will replace expensive commercial systems which cost about €5,000. And you can see here some of the data. You know, if you compare a commercial potentiostat, expensive potentiostat, and the data that you would get, and then compare it against the Tyndall prototype, and you can see the difference, significant difference between a healthy plant and an infected plant. I suppose one of the things that we're spend a lot of time doing is looking at how do you integrate all the sensors together, and in one area looking at smart capsule technology. And capsules can vary from large capsules down to swallowable capsules. So here's some of the guts of these various sensors, various the battery, communications, and so on that are built together. And the other thing that's important for us is, when we build these prototypes, we have industrial design which comes to the table, so that the prototype that you're delivering to an end customer looks like something that could be manufacturable, rather than something that has a lot of wires that most of us are familiar with creating. And we've gone through a number of generations for this. In the first case, we looked at irritable bowel disease in humans. This was about 20 years ago, and the capsule we made, it wasn't swallowable. Well, a pig could swallow it, but none of the humans who were working on the project were able to. So we had a lot of work to do on that. This project here was looking at actually using a capsule that could be put into a bio-pharma process, into vessels that might be used for drug development, or in fact in one case for development of soap solutions. And the capsule is able to communicate out through the vessel walls, but also you can vary its buoyancy so it can go up and down inside in the vessel, which would be really, really valuable, instead of having maybe lots of wired sensors going in and out, such a system. And then most recently we have got a European project which is working with a very famous institute in Strasbourg with the idea of developing the true swallowable capsule that would look at problems in the gut, and could ultimately perhaps have let's say a chemistry lab at the front end, or a lab on a chip at the front end of this unit. And in fact, the the end users that we're working with here, one team is in the Ukraine and the other team is in Kenya. And I guess particularly in Kenya, you could understand why something like this might be far more valuable than a complicated technology, you know, gastroscopy or endoscopies and so on. And of course, again, using the same platform, and this is the good thing, using the same platform, we were able to provide a bolus that could be put in a cow's stomach and monitor pH, temperature, dissolved oxygen, glucose, motion, and so on. And with a view to trying to determine how we could actually perhaps improve the feed for the cow that might actually result in reduced CO2 emissions. And, you know, I guess what's interesting then is to follow almost a 20-year program going from the early work we did. And while we weren't successful there, we stuck with the basic concept to deliver multiple platforms. And one of the most important things that actually fitted with that story is, you know, we have people undertaking very fundamental research on the sensors and various other aspects. But unless you can provide high quality prototype capability, you're not going to deliver the innovative impact that can be provided. And that can also lead to perhaps startup companies and products that can be licensed. Okay, so let's talk maybe a little bit about the idea of intelligence at the edge. So, you know, a lot of the artificial intelligence or machine learning that's going on at the moment and that's providing us inference in relation to sensors is actually coming from the cloud. And the problem with that is, one of the problems is you're communicating back to the cloud, so that takes time, so you're not getting real-time information or decision making, and you're also using a lot of energy. So if we could actually do all of this locally in this smart sensor, it could have major benefit. And here's some of the data that's quite interesting, I think, in terms of, you know, if you're trying to train AI systems and you're doing it via the cloud, the amount of time that's being taken is enormous. And also, if you look at the amount of energy that's being used through these data centers, you know, it's larger than some, I would consider major countries, the amount of energy across the globe, and also the amount of CO2 emissions that are being utilized. So that is not a sustainable model. So unless we start moving to actually developing AI solutions at the edge that don't use a lot of energy and that don't actually need, you know, let's say the models that are developed can be done with very small amounts of data. And I think this is an interesting schematic here. You know, what we're trying to do, you could say, is, you know, maybe mimic this idea of the human eye to the brain abstraction. You know, when I'm looking at you guys here, I'm not, you know, using up a data center energy with my brain. Okay, so there's some, you know, dramatic 10 to the 5 abstraction of what we're seeing. And it's the same thing if we're going to use this artificial intelligence at the edge. So the things that we need then would be power efficiency, learning, and it needs to be efficient learning using very limited data sets. But by following this model, and this is a combination of hardware and software, combination of electronics people, computer scientists, and actually mathematicians who perhaps have been neglected in this whole area. And our aim is to, over the next, say, 5-10 years, to make 10 to 100x improvements. That's what's going to be needed if we're going to use AI effectively on the edge. So now we have something that's very intelligent. We need to power it. And I've shown earlier that if we're powering, we cannot necessarily rely on batteries completely. So we need micro-energy generators, generating energy, harvesting energy from the environment, whether it's from light, from vibrations, from temperature differences, pressure. We need perhaps microbatteries or supercapacitors or fuel cells, and then we need some intelligent power management associated with that. Here's an example of some work that one of our colleagues, Professor Scheibel-Roy, did. And he was looking at using electromagnetic vibrations in order to power various entities. And he starts with a macro model or device prototype, but ultimately wants to get down to a micro MEMS device. Now it's interesting then, the big question you have to ask is, well, how much energy am I going to get out of this, or how much power? And if we want to operate in that Internet of Things space, we're talking about the need of maybe 100 microwatts to 1 milliwatt. And in some cases, some of these solutions here are in the range of maybe 1 to 50 microwatts. So there's still work to be done in terms of improving the technology. A number of my colleagues have already spoken about thermoelectrics, and we think this is actually a very good technology. It's very compatible with silicon technology, and we can also develop it on flexible substrates, so that it could be used with wearable technologies, where we might be using body temperature as the power source. So if you imagine with bandages that might be on the body, we could actually be powering entities. And again, what's interesting is going from the atoms right through to the systems. That's a critical element of having an understanding of all of those within a multidisciplinary environment. And the one thing I just wanted to mention here is, we have all the technology. We now have modeling that would allow us to model a particular deployment to see, do we have enough energy to drive the wireless sensor? And now what we're trying to do is we want to put together an energy harvesting testbed that could be utilized by different researchers, but could be utilized by companies who might have their own technology platforms, and they want to see how they would work within an energy harvesting testbed. So this brings me to an area that's I spent a bit of time working on. So, if you talk about the power management system specifications, and I don't know if any of you guys have worked in power electronics, but bottom line, if you go to a company and you say, I'll build you a power supply, they come back and say, yeah, that's great, and these are the specifications. So take up no space, cost nothing, last forever, zero power loss. I mean, we're engineers, of course we can do this. And let me then take you on and just present you with a story, right? So here is an iPhone from a certain fruit company. And here's the processor chip, okay? And this particular chip, it was being powered, and normally these processors, they have multiple power rails. So they're being powered by a power management chip here, which has a large number of linear regulators, but it also has a large number of DC-DC converters, different voltage levels. So it's coming in from the battery at whatever, maybe 4.55 volts, and then it's delivering various voltage levels into this, from maybe 2 volts down to 1 volt, and ranges in between. And so you see here, there's a whole range of these inductors for these DC-DC converters, switch mode converters that have output inductors. And These are actually bulky components. They take up a lot of space. They have a large height. And it would be great if you could get rid of these. So a while ago, we wanted to look at, could we get rid of these inductors? And if you think about magnetic disk heads, they used thin film magnetics to read and write memory. So we were thinking, well, that's thin film magnetics, that would sit on silicon, but we need it to deliver current now as well, not just signal. So could we do that? And so we set out trying to do that. And could we build these tiny components, 1 millimeter square or less, that are only about 100 microns in height? And we spent quite a lot of time working on this, and I just want to show you what has happened in the industry in the last year. So here's what I showed you earlier, right? Going back to 2018. And if you have spare money and you want to buy an Apple Mac Pro, and you have someone who can take it apart carefully, then you will find inside in it, this is a cross-section of the microprocessor here. So I'm say, taking a cross-section of that of the microprocessor, which is here, right? So this is the new system, and I'm taking a cross-section. Here's the microprocessor. It's got a heat sink sitting on top of it. And then here is the printed circuit board that it's sitting on. Okay? And these guys here are actually miniaturized vertical capacitors. And down here, you have this guy. So here's a power management chip, and sitting on top of that power management chip are a very large number of inductors. Coupled inductors. And so what has happened in 2021, as I said, this fruit company went from this solution to actually embedding completely within the microprocessor package. So as I said, if you have spare money, you can try and reverse engineer this. But why would you want to do this? Well, the reason you want to do this is, if you could do it, you could actually set up a nanogrid inside in the microprocessor with a large number of different circuits being controlled separately by separate DC-DC converters. So now I can turn on and turn off these individually and thereby save significant energy. So in that particular Mac Pro, that operates for about 17 hours, which would be about maybe twice as long as would have previously been possible. And we are seeing an increasing number of companies interested in working in this space and bringing this solution with the view of reducing the energy utilization. And here are the range of companies that operate in this space. You could say this is the supply chain, and if you look at the companies, these are not standard inductor companies. These are all semiconductor-related companies. Some of them here are the semiconductor foundries, the systems companies, IC design, power management companies, and so on. So what we are beginning to see is a transformation in the nature of power management. But if I go back to the, what did I say? Cost nothing, take up no space. Well, the technology we have, you could say, is magic. And it makes magnetics disappear into the silicon. A bit like CMOS made transistors disappear. And so here are some of the examples of, processed on top of silicon. Here I have a magnetic layer, then I have electroplated copper conductors for the windings, and then I have another layer of magnetic material so that I can enclose the windings, giving me a structure like this. So this is a solenoid version. Here is what I'd call a strip line version. and you can even, double up on the conductors and so on. So, to achieve this, integrate the power with the load, we get this granular power grid or nanogrid, delivering multiple voltage rails, dramatically improves the transient performance and increases system efficiency. And we have been doing this for a while and have licensed that technology to a number of entities very successfully. And if I just talked about it before and after, the before was 1994, and large wire-wound inductors, and this is the after. This is the after. This was the before. So I was talking to Michael and some of his colleagues yesterday, and I suppose the one point that we brought up was, if you want to do research, you really, really need to want to do it, because you may turn out like this. Okay, so then if I move on to this idea of a sustainable Internet of Things, what does that mean? So when I started out looking at this maybe about 10 years ago, I thought I had a great phrase, deploy and forget. And then my environmental green friends said to me, we're not working with you if you're going to deploy 1 trillion sensors and leave them out in the environment. So I said, all right, I'll get 1 billion drones to retrieve them. Of course, that's not economically feasible, right? So then I came up with a new idea, and my boss loves it. It's just like deploy and dissolve, which is what you would want to do with electronics, right? Now, the only problem is maybe the monsoon season here might disrupt your system a bit, but in Ireland, if it isn't raining, it's thinking about it, okay? So you would really need to develop some very smart materials with umbrellas, micro, nano umbrellas, whatever, to enable something like this. But on the other hand, right, doesn't it make sense that, this is where some of the research should be moving? And so, this idea of, the existing life cycle of electronic products, right? We start with raw materials, we put in energy, and then we go and manufacture everything, and all the manufacturing has an environmental footprint, and there's a massive amount of waste globally, having a significant environmental impact. And not just with the waste, but with the manufacturing and so on. So there is a way to achieve low environmental footprint, and some of our colleagues have been working on the idea of laser-induced graphene from bio-based materials. So here's a cork, and they have actually been able to laser impress electrodes, let's say biochemical or chemical electrodes on the surface of this using laser. In fact, another very good example that one of the guys did, he took a substrate, I'll tell you what it was in a minute. He took a substrate, he created the laser-induced graphene microelectrodes. He did his measurement, and then he took it and he dropped it into water, and it dissolved, right? And it was a vitamin C tablet, right? So, it's not as if this stuff isn't out there, right? But maybe we haven't been thinking about it. So the future life cycle then, right, would be, can we go and do a rethink? So we now need to think about, raw materials and energy are a resource. They're a limited resource. And their utilization is impacting the planet. So we need to consider, how do we actually rethink the whole electronics ecosystem, you could say, to see how we reduce greenhouse gases, water usage, toxicity, ozone depletion, and so on. So I'm going to finish at this point. And I suppose my view is, right, that this Internet of Everything, it will transform our society and our management of planet Earth for the better. And that's the most important thing, right? Is it going to improve things? And I believe it will, from health and well-being the built natural environment, transport, communications, infrastructure, education, manufacturing, agriculture, food production, protection of the environment. And therefore, it's something that's really important to be working on. But this requires R&D. If we're going to deliver these autonomously powered, intelligent wireless sensor systems, we need a multidisciplinary approach from atoms to systems. It needs to encompass hardware and software. And as you saw earlier, it takes time. And I think sustainable electronics will be essential in this future. Thank you very much for your attention, and I'm happy to take questions.